A STRIPS representation may have variables. State does not have variables. Preconditions, effects may have variables as well. So action is going from going from to using P. So I'm flying a plane P from a airport who is referred to as from and to an airport which we are referring to as to. The precondition here is at P from and plane P and airport from and airport to. So I need to fly a plane from P to from to. I need to first check whether from is an airport, to is also an airport, P is a plane, and the precondition should be I should be at from, or the plane should be at from. So at P from indicates that plane is at airport from, the plane is P, airport is from, and airport is to. So these are the things that we are that needs to be met if I want to fly from to, okay, using plane P. The effects of flying a plane P from to will be that at P from will no more be a true value. Instead, not at P from will be true, and hence this effect will mean I should remove from the state at P from of the world. Okay, it's not removed from the precondition, it is removed from the state of the world. So the effects can also be located in the preconditions, or effects can be located in the state and they might not be there in the precondition. At P2 in this case is not there in my precondition, because at P2 is a newly generated atom which says that now plane P is at airport 2. Okay, so this is how we represent an action. So I give you a minute or so to think about it, whether you understand the representation of an action. So representation of an action requires you to write an action schema. Action schema involves writing three things about the action. First is the action name and the parameter list. Second is the precondition which needs to be satisfied if we want to apply the action. And the third thing is the effect of the action, which indicates what are the assertions that I need to remove from the list of assertions that compose the state, and what are the assertions that I need to add to the list of assertions that composes the state of the problem. Okay, so the effect is a conjunction of function-free literals describing how the state changes when the action is executed. So effect is a conjunction of function-free literals. So as they are function-free literals, they can be part of the state. As I add certain literals to my state, like not at P from, wherein at P from is already there in the state, these two get cancelled out because A and not of A is going to be true. Okay, they both can't coexist. So I have to remove at P from the state, as not at P from is now true. And not at P from, we do not use any negative literals in strip representation. That's a strict thing in the strip representation. We never use the negated literals. We always use positive literals. A positive literal P in the effect is asserted to be true in, and this in is the state resulting from the action. Whereas, I just need to increase the font, excuse me. Okay, the state resulting from the action, whereas the negative literal not of P is asserted to be false. This is asserted to be false, and hence I need to remove it from the variables in the effect must also appear in the actions parameter list. So this is how we actually do apply certain action. So how you define the action schema. So what all things we have seen so far is we require to define the state, representation of state. We need to define, or we need to know, or we need to write goal satisfaction, which is like a subset operation. And if I want to program it, it will be just a subset operation. And this is why we are writing it in propositional logic. We are making our lives easy in checking the goal satisfaction, because that is going to be there when am trying to apply any problem solving state space problem solver for that matter. Okay. Now the third thing that we need is representation of action, which means understanding to write action schema. Action schema involves three things: action name with parameters, list of a list for that particular action, preconditions, which are the conditions that need to be satisfied by the state of the world if I want to apply the action, and that will be checked against if I want to apply the action. Those actions for which the preconditions are met can be applied at a particular stage of the problem. And once the action is in effect, the effect of the action gets generated. The effects may or may not have positive and negative literals. And these positive and negative literals means the positive literals are asserted in the state, negative literals are removed from the state. And that is why they refer in some of the problem solvers, we say we generate two kinds of lists. One is add list and the other one is delete list. All the positive assertions or P kind of assertion items are going to be in the add list, and not P kind of assertions will be in the delete list. Okay, so this is how the action schema is. Now the next thing that we need to remember, or we need to understand, is how these actions actually take. So I have actually discussed this, but I'm going to go a bit in details. First, we say that an action is applicable in any state that satisfies the precondition. Otherwise, the action has no effect. Okay. For the first order action schema, establishing applicability will involve substitution. Now, so far we had considered that we have just the propositional representation of state, propositional representation of precondition and action, but we may also have the non-propositional or first order logic representation of state. Now this example, which is over here, suppose the current state of the world is described by 1, 2, 3, 4, 5, 6 predicates handed together or conjuncted together at P1 JFK. That is, plane P1 is at John F. Kennedy Airport, P2 is FO, P2 is plane 2 is at San Francisco Airport, P is a plane, P2 is a plane, airport JFK. So JFK is an airport and SFO is an airport. So at P1 JFK says P1 is at JFK. P2 at P2 SFO says P2 at SFO. P1 plane indicates that P1 is a plane. P2 plane indicates that P2 is a plane. JFK is an airport and SFO is an airport. So this all 1, 2, 3, 4, 5, 6 predicates together indicates my current state, which says that there is one plane at JFK and there's another plane at SFO, and both SFO, JFK are airports and P1, P2 are planes. This whole information is captured into this state representation. This state satisfies a precondition at P from and plane P, airport from, airport to, where the substitution that I use for the variables are P small is P1, from is JFK, and to is SFO. So this is nothing but the unification procedure that we learned. So we just use substitution in order to satisfy the precondition. Okay, so we already said that in the state representation, this is the state representation, there are no variables, but in the precondition representation of action, I have variables. So to match the precondition to the state representation, I'm using substitution. So now the substitution will be used in this particular manner, okay, which is very much what we learned in the predicate logic inference techniques. Okay, now the result is state S that starting in state S, the result of executing an applicable action A is state S dash, that is same as S, except that any positive literal in the effect A is added to S dash and any negative literal not P is removed from S dash. Now, if we consider the current scenario, the state at P1 JFK, now we are actually having precondition that P1 is at JFK and 2 is San Francisco. P1 will be flown over from JFK to San Francisco. As P1 flows over from JFK to San Francisco at P1 JFK is now negated. Okay. At P1 SFO is now asserted. Okay. And all the other things remain the same. So at P1 SFO is now there in my state representation. At P2 SFO remains there, P1 remains there, plane P2 remains there, airport JFK remains there, and airport SFO also remains there. So now this is going to be a very simple way of looking at how actions now are making you walk over the state space. So I have a state, I have action schema, I use substitution to select applicable action. If I apply an applicable action, I need to use precondition to check whether the preconditions are substitution to check whether the preconditions are matched. If the preconditions are matched, the effects are triggered with the substitution, and since the substitutions are now in effect, we can know what literals to remove from the state and what literals to add to the state and generate new state representation. So we start from state S1 here. Okay, we have this action once preconditions matched using the substitution theta, which will generate the action fly P1 JFK SFO and which will make us reach to the S2 as our resulting state. So this is how now we have a complete kind of an algorithm, which first will check if the current state is matching the goal state using, now goal is not a state, goal is a representation, by checking goal satisfaction. So we'll check goal satisfaction. If goal satisfaction is there with the current state, we will do nothing. We will just have a back pointer and we'll know how we reached this particular state. If we have not satisfied the goal, we will now try to figure out using the state and trying to use the unification for every precondition of all the possible actions. Some of the actions, the preconditions could be unified with the current state, and those actions are now alerted or those are initiated, and one of those actions now will be carried forward. Now the action that I carry forward will be executed and the results will be computed to generate another state. Now if you look this in a visual or a graphical manner, you will understand that now you have started walking over a state space. As we generate new state, we will check whether that particular state satisfies the goal. If it satisfies the goal, we stop the process. We already have back pointers, we'll maintain those back pointers and we will walk reversely to initial state and get our action sequence. Okay, so this would be the way a problem will be solved in a forward sequencing. I'm going starting at the initial state, I'm going further on the state space, walking using the actions which are possible, using now the state space representation of a planning problem using logic representation, which may use propositional atoms or predicate atoms. Okay, please understand, if I'm using propositionalized knowledge base, then all the actions schema will also have prepositions. They won't have predicates. Okay. Now the next thing that I need to remember over here is, I'm not going into this detail. We are going to check these particular two differentiation points, and this is a good question for any sort of internal test question or an Viva oral questions. Although ADL is not there in your syllabus, STRIPS is there. So we are listing out important points where STRIPS scores over ADL. So ADL stands for, I had given you what it means yesterday. It is abstract data representation language or something like that. STRIPS, we know what it is. It is Stanford Research Institute problem solver language. Okay, we only use positive literals for an unknown. We may have positive and negative literals mixed in ADL. So that's the beauty of ADL. We can mix positive and negative literals together. STRIPS has closed world assumption. That means unmentioned literals are false. And in literal, I don't mention in the state representation is always false. ADL, on the other hand, does not say or does not assume the closed world assumption. So for it, the world is open. The literals which are not known or which are unknown, their truth values are also unknown. Unmentioned literals are completely unknown. The truth value is not known. Effect P and not Q means we need to add P and remove Q from the state representation. Effect P and not Q means add P and not Q and delete not P and Q. So now it's natural that in ADL we are doing extra operations than strips, because both say are generating effects P and not Q. In strips, I just need to add one thing and delete one thing. On the other hand, in ADL, I need to always do take care that both the assertions P and not Q should be added, and their negated versions, not P and Q, needs to be deleted. So extra operations are there. Fine. Then in strip language, only the ground literals are there in the goal, whereas in ADL, we can have variables and quantified predicates as well in the representation of the goal. So यहाँ पे एग्जाम्पल दिया हुआ है स्ट्रिप में, जो प्रपोजिशनल गोल का एग्जाम्पल है. इसका मतलब ये नहीं कि स्ट्रिप्स में प्रपोजिशनल गोल होते हैं, लेकिन प्रपोजिशनलाइज्ड प्रेडिकेट्स भी हो सकते हैं गोल में in the strip language. Please understand that goals are always conjunction in the strip language, whereas goals allow conjunction and disjunction both in ADL language. That's another thing that ADL allows. So strip is in this particular issue or in this particular property, ADL scores over strip because ADL is now able to represent more things easily because we are allowing two different connectives, which means that a lot of things can easily be encoded, like implication, like bidirectional. Because if I want to have implication realized or represented, then in ADL, I can directly apply the implication removal formula and I'm done, but not that much, that easy for the strip language. Okay. Next thing is that effects are conjunctions. So effects are always conjunctions in the case of strip. Conditional effects are allowed in ADL when P colon E means E is an effect only if P is satisfied. So precondition P is satisfied, then only E is the effect. So there is no way to represent equality in strip language because we are not having variables as such. But in ADL, that is possible. So it is more closer to a generic representation, ADL. There is no support for types in this strip, whereas ADL, there is a way to represent different types for different objects in ADL. Okay, so that's the difference between two representational languages, ADL as well as strip. Now, this is an example of an action represented in ADL. So we are saying action fly P colon P plane. So here we are directly saying that P has a type plane, from has a type airport, to has a type airport. So considerably number of things that we had there and it together will now get reduced, because we had to say that P is a plane precisely in strips. Here we are saying that P has a type plane. So there is some kind of an aggregation relation that we are defining, and that will make our lives easy. Okay, ADL is not there in your syllabus, so don't worry about what it means, how it is written, and will I be required to write things in ADL. Okay, so the full form of ADL is action description language. Okay, so we describe action. So just for your information, preconditions here is that P should be at from, and from should be different from to, then I can fly from P to 2. Now this was not the case, or this I could not do in case of strips representation, because there was no way to check whether the from and to are equal or not. Okay, fine. Now the effect is also realized in a different manner, so resultant will also be different. So there are many different planners available. So this is planning domain definition language, or PDDL, another variant language which is not there in your syllabus. So EDL, PDDL are not there in your syllabus. This is an important thing. This we'll leave our lecture today at this point, and we will talk about this tomorrow. So I'm going to leave you with 2 minutes looking at this particular slides at the end of this recorded session. As I told you, I'm not going to have a full lecture. I am just taking forward the topic, and I don't want you to lose interest. That's the important thing I'm doing over here. So see, what we have here is, we have init, means this is an initial state, and this init starts at this point and this ends over here. Okay, this init has 1 2 3 4 5 6 7 8 9 10 predicates, which says C1 SFO is at SFO, C2 is at JFK, P1 is at SFO, P2 is at JFK, T1 is a cargo, C2 is a cargo, P1 is a plane, and P2 is also plane, JFK is an airport, SFO is an airport. So now this naturally is a cargo transportation problem. There is some cargo at a particular airport, and there is some other cargo at some other airport, and we want to move a particular cargo from one place to the other. So what we want as a goal state is C1 should be at JFK. So C1 cargo, which is currently at SFO, should go to JFK, and C2 is the cargo which is currently at JFK, should come to SFO or San Francisco. So I need to fly the cargo from SFO to JFK, and cargo C2 from JFK to SFO. So that is what a normal person or a human being can understand from this. Now, for doing so, I need to define action schema, and my action schema will have over here, I guess, 1, 2, and 3 actions. So I have defined 3 actions over here. Okay, the first action is the load action, which loads a cargo in a plane at an airport. So I load a cargo C in a plane P being at an airport A. Okay, so this is what we do in the load action. Unload action, we remove cargo from plane P at an airport A. So now when I want to transport cargo C1 from SFO to JFK, I need to first load cargo C1 in the plane which should be present in SFO, and then we should fly the plane from SFO to JFK. So I need load action, then I need fly action. Once I reach the destination or destined airport, I can unload the cargo. So load, unload, and fly. These are the 3 possible actions that I require. Now the rest of the things are in front of you. I leave it with you what these things are and how these preconditions are defined. Things to note or things to remember based on the discussion done today is the init, or the initial state that I have represented. So init is the name of the state, and all the other things which are conjuncted together or ANDed together are nothing but the predicates, and all you will check that all the predicates are grounded one. That is, the parameters are ground terms, be it binary predicate or unary predicate, irrespective of that. Now, the second part of my definition of planning problem is the goal. So the goal is defined as conjunction again of multiple ground literals. We are again having ground literals over there in the predicate. So ground terms are there or atoms are there. So since there are atoms, I can modify them. So at C1JFK is an atom, at C2J SFO is an atom, and they are ANDed together. And that is something like a subset of the all atoms that make up a state. Fine. Then we talk about actions, and actions, we are evident that in the name itself of the action and the parameters of the action, we are using variables. There are small case letters CPA, CPA, and P from 2. So we have already learned about action fly P from 2. This is exactly the same action. We generate delete list and add list in the effect. Okay, effect also can have variables, precondition also can have variables, and the action name can also have variables. Okay, fine. So we will stop here. I hope you will be able to understand the content that I have discussed right now. I hope you will look all the 3-part session that I have recorded before tomorrow's lecture. So tomorrow we'll be having lecture. I'm not traveling tomorrow. I'm at home tomorrow. So tomorrow we will be positively be having lecture at 2 o'clock. So before that lecture, I would request you to watch these 3-part video or 2-part video, whatever it is composed of, so that things will be easy for me as well as you to understand. Okay. Thank you.